All right. Hey, another day, another lesson. So we kind of started this last class where we talked about the titration curve of a strong acid versus a strong base. I figured, let me just give you a little review in terms of what's happening. So in this case, this is known as a titration curve. What it's illustrating is that you have some sort of acid in there to begin with. Okay, so let's say there's like 0.5 molarity of it. Okay, at a certain amount, I don't know, but it's 0.5. Usually this is an unknown. Okay, and you're just only given the volume, but let's say you already know it's 0.5. And it's reasonable that the same amount of moles of KOH is going to be used to create an equivalent point. Okay? So let me draw a little burette. A little valve. Okay? So what's in here, of course, is 0.5 molarity of NaOH. Obviously, I made it 0.5, so therefore it is easy for me to look at the volume. Because if they have the same concentration, whatever volume is in here, okay, let's say it's 50 milliliters, you're going to use 50 milliliters of this, because by doing that, you have the two moles being equal. And that is what we call equivalent point. That is the end point, okay, in your titration lab. So obviously you go drip by drip, okay, to react with the acid. And what you're doing is that you are creating KCl and you're creating water. Okay, so every time you drop some of these, oh, did I write NaOH? Why did I do that? It's supposed to be KOH. Okay, when you drop KOH into hydrochloric acid, what you're doing is you're creating KCl and you're creating water. Okay, so little bit by little bit, the concentration of this is going to be going down. This concentration of this will be going up. Okay. And what we want to monitor is the pH, because HCl dissociate to give you H plus and Cl minus. Looking at H plus, well, every time you add KOH will also dissociate to give you K plus and OH minus, right? The OH minus will take away the H plus from HCl and turn it into water, which is, hey, exactly what one of the product is. So you can see that you started off with lots of H plus, but as you add KOH in there, the amount of H plus will start to decrease. Hey, if the concentration of H plus is decreasing, pH will be increasing. So that's why as you add more and more KOH, the pH is increasing, is actually becoming more and more towards neutral. And then you'll see this very, very sharp turn when it's equal, when it's at equivalent point. 50 milliliters is at equivalent point. If these guys are at the same concentration and you have 50 milliliters of acid in there, well, it only makes sense that you need 50 milliliters of base to reach equivalent point, where the amount of HCl in mole and the amount of KOH in mole will be equal. Right? If this is 0.5 molar, this is 0.5 molar. If you started with 50 milliliters here, wouldn't it make sense if you use 50 milliliters of this to reach equivalent point. Because if you think about it, this will have a certain amount of mole. This will have a certain amount of mole. Since the numbers is equal, they're going to be same. Okay? But that's not what we're interested in. What we're interested in is the pH. For strong acid and strong base titration, the pH is going to be 7, which is neutral. Now, the reason for this is all of the HCl is a reactive, so there's no more H plus floating around. If you don't overshoot, there is no OH hanging around because they all became water. They all became KCl. Can KCl react with H plus? No. Can KCl react with OH minus? No. Okay, KCl cannot react with H plus or Cl minus, OH minus, because K is a metal that makes up a strong base. Cl is a non-metal that makes up a strong acid. So these guys are no conjugate. So therefore, this guy is not going to make your solution acidic or basic. It is going to be 7. But you'll see later on that the salt that you make have the ability to make your solution acidic or make your solution basic, okay, by doing hydrolysis. But in this case, nope, KCl is going to be neutral because this guy right here is the metal of a strong base. This guy right here is the non-metal of a strong acid, and they just don't do that. So that's why the equivalent point is going to be 7. Okay? And just like what I've mentioned here, these numbers, yes, the volume added is 50 milliliters because originally there's 15 milliliters of acid added in here. Okay? So when you're titrating, what you're doing, of course, when you reach end point, is that the mole of acid equals to the mole of base. That's when you hit equivalent point. But let's just say you continue to add more and more and more base. Obviously, you're going to have more KOH, an excess of KOH. An excess of KOH means an excess of OH. An excess of OH means basic. So as you can see, if you decided to go over the equivalent point, the pH will have a little sharp turn right here. And as you can see, you're going into the basic route. It's going to get more and more basic. Okay, so that is strong acid versus strong base titration curve. It makes this thing we call an S shape. What if we didn't use strong acid? What happened when we turn this into a weak acid? How would that differ? Well, let's go over to the next graph. This is a weak acid titrating it with a strong base. The weak acid will be acetic acid. The strong base is going to be sodium hydroxide. And what you're going to get? You're going to get this salt called sodium acetate. Unlike this salt that remains 7, this salt is not going to do that. No. This guy is a metal from a strong base. You're not the culprit. No. You're not the culprit. You're a good guy. Not this guy. This is the non-metal that makes up a weak acid. Unlike Cl, which is the non-metal that makes up a strong acid, this is the non-metal that makes up a weak acid. this guy can do something to this guy and say, hey, water, we can do something together, can't we? Let's take a look at the curve. Now the curve is a little different, as you can see. First of all, you started at a higher pH, because this is a weak acid that is in the flask. It's not gonna dissociate completely. You're not gonna make lots of H+, because this guy is more predominant in the equilibrium, shifting more to the left, as you want to say it. So you already started out at a higher pH than a strong acid will. Second of all, the curve. Okay, as you add strong base into this, you're going to have an increase of pH at a higher rate. Why? Le Chatelier principle will start to come into play. This guy fully dissociate. This will say to this guy, hey, give me more H, give me more H, give me more H. Remember, in Le Chatelier principle, this guy dissociate. However, you're not going to get fully dissociation. You're going to make H+, but you're going to make H+ according to what this Ka is. But as OH from NaOH keep taking this away, and keep taking this away, and keep taking this away, this guy will say, oh man, I need to re-establish my equilibrium, so I'm going to keep making H, keep making H, keep making H, while you keep taking H away until I'm all gone. Until the mole here equal to the mole here. Same idea. Hence, of this increase in pH. Now, the equivalent point is always, like we see here, the middle of that sharp turn. Well, that's not so middle. In this case, the middle is a smaller section. Okay? And what you'll notice is that if you take the middle of this section, the pH here is slightly basic. Now we'll take a look at why that is later, but we're going to put our attention a little bit towards this area. This area right here has a special name, and it's called buffer region. Now we talked about buffer in the last class. Okay, last class we talked about buffer. How does a buffer work? How do you make a buffer? Now, if you remember, if you go back to this slide right here, to make a buffer, you can take like, say, like a weak acid, in this case, a weak acid, and if you insert half the amount of the strong base to react with this weak acid, you'll make a buffer. Oh, right? Check out this curve right here. This is called a buffer region is because at this point, okay, between no base is added to equivalent amount of base added, this region right here can be used as a buffer, especially midway through. Okay? This is known as half equivalent point. At half equivalent point, it has a certain pH. This pH is actually equal to what we call the pKa of your acetic acid. Remember, all weak acid has a certain Ka value. That's the dissociation constant. If you were to react your weak acid with a strong base like you see here, and you go half the equivalent point, at half the equivalent point, the pH that you get is actually the pKa, which is the negative log of what Ka of acetic acid is going to be. That's a very, very important thing to think about or to keep in the back of your mind. How do you find Ka? Simple. React half the equivalent point amount of a strong base and figure out what that pH is, because that is the same thing as the pKa of that weak base. Inverse log this and you'll get Ka. That's how we find Ka. Now, not only is that important, but another important factor, of course, is that at this point in time, when you add half the amount of equivalent volume, this is a very good buffer. That's why this is called the buffer region, because potentially at this point, you can make a very good buffer, which makes sense, right? Which makes perfect sense. Let's say you have 0.5 molar of this, or I don't know, 0.5 mole of this to start with. Half the equivalent point, you would have added 0.25 mole of this. Hey, wouldn't this combination make up a terrific buffer? Because that's what we did last time. We started with 1 mole of this, and we added half a mole of that. We end up at equilibrium this situation, which is a buffer situation. So a lot can be learned about this curve. This is a very important curve. But let's continue. Okay, let's continue. Why is the equivalent point or the equivalent pH, we know the equivalent point, this is when the mole of this equals the mole of this. Let me just get rid of these numbers. Okay? But why is this not 7? Isn't that a salt? Well, as I said before, this dude right here, he's not a normal dude. Okay? Unlike this situation, where I am an anion of a strong acid, I don't want to touch you. However, I am an anion of a weak acid, and I certainly want to touch you. How? Check this out. CH3COO minus certainly would love to react with H2O. And they will go through a second reaction, actually, a continuous reaction of making this back. Because naturally, I'm a proton acceptor. If you're a proton acceptor, water says, I guess I have to be the donor. By being a donor, you're making OH minus. So OH minus in this system causes the pH to rise. That's why this guy is not pH of 7, because this has the potential of reacting with water to create OH minus, which makes the whole mixture basic in nature, which I illustrated right there. The difference is I forgot that this can't go backward too. Okay? Now, you're not going to make a lot of these. Don't get me wrong. Okay, this is very important to note. It is an equilibrium, which means this is more predominant. This guy will react with this guy. But you're not going to say, oh, every time you make these, you're going to make these. So the concentration of this and this is the same. No. Of course not. That'd be crazy. Then the curve will not look like this. The curve will probably look more like this, where this is the equivalent point. Okay, but that's not the case. Okay, yes, they will react, but very sparingly. You're not going to get a lot of these. You're going to get just a little bit to give you that little bit of a basic boost. So it's very important that you mention it's an equilibrium and not a full arrow like that. Okay. All right. So that's what happened in a weak acid versus a strong base titration curve. So what about the other way around? A strong acid with a weak base titration curve. So again, same idea. You started, of course, with some acid. That's what you're starting with here. It's a strong acid. So that's why it's so much lower here than here. Okay, you're starting with a strong acid. As you added weak base into the strong acid, obviously, like any neutralization will occur, you're going to have the pH increasing until you're approaching equivalent volume. In this case, it's 25 milliliters. So let's just say this is 0.5 molar, this is 0.5 molar. Okay, if you started with 25 milliliters of acid, you're going to use 25 milliliters of base, because that's just when this mole will equal to this mole. But as you monitor your pH, you'll notice that at equivalent point, the pH is not 7. It's actually less than 7, which means your equivalent point is acidic in nature. The idea is very similar to this situation, where the equivalent point is basic in nature. Why? Because of this dude. In this case, why? It's because of this dude. NH4Cl do fully dissociate because it's aqueous. NH4 will react with water inside this aqueous system and turn himself into NH3 and H3O. Why? Because NH4 naturally is a proton donor. Hey, if you're so willing to donate proton, water will say, I'm very willing to accept your proton because I'm a nice guy. You donate, I accept. Because of that, you're going to make H3O. This will cause your solution to be acidic. Hence, every NH4Cl that you make, there is potential that you'll make a little bit of these, causing your equivalent point to be a little lower than 7. Sort of like the opposite of the last slide. Hopefully you understand that. Now, what if you do this when you take a weak acid and a weak base and you put it together? So you have acetic acid reacting with ammonia. Well, this is where it kind of counteracts, okay? It's like you're the bad guy that's not making things 7, but guess what? I am a bad guy too that is not making 7. You tends to jack up the pH. Well, I tends to lower the pH. Eventually, we sort of cancel each other out. So when you take a weak acid and you react it with a weak base, well, you are going to make your equivalent point being 7. As you can see, you will start out at a very high pH, and you'll actually end at a lower pH. No, well, I don't know how to say it, but then you'll start out with a higher acidic pH, but you'll end at a lower basic pH. How's that? Now, is it always 7? Is it like this situation where it's always 7? No, this situation is always 7 because this guy fully dissociate, this guy's fully dissociate. This guy doesn't say anything to this guy because they're not friends. In this case, that's not entirely true. Okay? The pH of this does not always necessarily have to be 7. It all depends on the Kb of this and the Ka of that. Okay? All depends on the K, or you can say the Ka of this or the Kb of this, because they're going to be different. They're always going to be different. Changing this will make the solution, will make the curve a little different, depending on, hey, do I dissociate more often or you dissociate more often? Okay, when we do make this, what is the strength of me reacting with water versus the strength of you reacting with water? It all depends. Anyway, in our next lesson, I'm going to show you how to do this. I'm going to show you how to, on paper, monitor the increase in pH as you add more and more base into your acidic solution. Then the following lesson, I'm going to show you how this works on paper. How to calculate the pH as you add a little bit of base into your weak acid. There's going to be a lot of calculation here, so get yourself ready. Same with this, but not as much as the other. Okay. Let me stop here now, and I'll see you later. Bye, everyone.